Welcome back to another calculus video. Today we're going to be talking about solving limits analytically in a variety of situations. So we introduced it a little bit on our intro video, but this is delving more into it because the majority of limits you solve are going to be involving algebra, and they're going to be the analytic limits. So understanding the variety of ways you can see that and what to do always helps with these problems. So the first type are the ones we kind of did introduce before. These are the ones where you can just plug in things. So for example, if we had the limit x approaches 1 of 2x plus 2, we can just go ahead and plug that in. We can have 2 times 1 plus 2, which of course is 2 plus 2, which is equal to 4. So as you can see, that also works perfectly fine. We got the value by plugging it in. However, we're not limited just by basic linear functions. We also can do something like this. So let's just say we had pi over 2, x approaches pi over 2. And what if we had the expression sine of x plus 4? So if we had that, we would say that it's going to be the sine of pi over 2 plus 4. And we know that the sine of pi over 2 is 1. So 1 plus 4 is going to give you 1 plus 4 is going to give you 5. Okay, so that also works just as well. And we also could do something like instead of trig or algebra, we could do something like we could utilize e's, for example, exponents. So we have, what if we had e to the x plus 1? So e to the 0 power plus 1. We know that e to the 0 is 1, so 1 plus 1 equals 2. We also don't have to have just a standard number at the end, so let's try e again, but let me just clarify it doesn't have to be so perfect. So if we have e to the limit as x approaches 1 from e to the x plus 2, let's say, well, e to the first power plus 2 would really just be e again, so it would be e plus 2. So the answer doesn't have to be just a sole number. We can, of course, write it as something that's indeterminate. For example, it doesn't have to be just a completely sole number. So you can have stuff like this, just very similar. You're plugging things in. But, of course, that's not where the problems will end. So after they give you problems dealing with simply plugging things in, kind of utilizing your other algebra knowledge, they'll give you certain problems where you can't just plug in directly. So for example, what if we had the limit as x approaches 5 of x squared, or x minus 5, I should say. So x minus 5 over x squared minus 25. So if we just tried to plug in here, what would happen? Well, if we put in 5, we'd have 5 minus 5, which is 0, which actually is fine. We can have a 0 on top. That would make it 0. But here's the problem on the bottom. If we have 5 squared minus 25, that will give you 25 minus 25, which is 0 again. The problem is that 0 over 0 is indeterminate. We don't know what this is exactly. It could be 0, it could be 1, it could be infinity. We don't really know what this is. So this can't be an answer. So we can't just plug in here. We have to change the function a little bit, which is what you'll see with all of these ones coming up. We're going to be manipulating the function a little bit so that we can plug in at the end. Okay, so if you had to guess, what should we do? Well, the answer is that we really need to change the bottom. The bottom is the problem, and usually what you want to do is you want to factor it with these standard ones with like a simple x squared term. So if we had like x minus 5, we can just rewrite. But if we had x squared minus 5, we can rewrite this. We can just factor it as x plus 5 over x minus 5. What we can do is we can go ahead and cancel these two, and what will happen is we will be left with the limit as x approaches 5 out of 1, since there's nothing on top anymore, of just x plus 5. So x plus 5, now we can solve this, because if we plugged it in, we'd have x 1 over 5 plus 5, which would give us 1 over 10, or 1/10. And this is the answer. So what's happening is here is this is giving you the f of value, the y value, as x approaches 5. So it's giving you the actual value. You just had to kind of simplify something in the initial function they gave you. Okay, so what if we had something similar? What if we had something like the limit as x approaches 2 of x minus 2. Oh, actually, let's not use, yeah, I guess we can use 2. So x minus 2 over x squared minus 4. So again, we have the same problem. If we plugged this in directly, we would get 0 over 0. Now if we factor this, we can get x minus 2 over x minus 2 multiplied by x plus 2. And again, as you can see, these things cancel. We are left with just this 1 over the x plus 2. So the easy way to understand this is we are simply taking something that already could be reduced, and we're just having its simplest form to work with. That's all we're doing here. So then if we plug in just like before, we have 2 plus 2, and then so our answer is 1/4. So the same thing as before. If you notice, it's very similar to when we plug it in. We just have to get it to a form where we can plug it in. Okay? So if you just have these kind of ones where we have to deal with plugging in with factoring, it also sometimes we need to deal with radicals, and this changes a little bit. So if we had something like limit as x approaches 3 of the root of x plus 1 minus 2 over x minus 3, what will we do here? Well, it's important to note that it's not the radical that's causing the problem. It's this denominator, just like before. Because if we put in 3, we'll get 0 on the bottom, and so that can't work. We can't have a denominator of 0 on the bottom. So like, for example, if we had a limit like this, but it was, let's just say, root of x plus 1, we could do this, right? This would be 3 plus 1, which is the root of 4, which square root of 4 is just 2. So it's not that the root is causing the problem again, it's the fraction, it's the denominator. And usually 0 is the culprit. So how would we simplify this? We can't factor, but what would we do? Well, the best thing to do here is to take what's called the conjugate. The conjugate is just taking the root, so whatever has the root, the expression of the root, taking the opposite of the sign. So it's a minus here, so we want to multiply both sides here by a root of x plus 1 plus 2, and we would do it for both of the sides here. Okay, so what would happen is we'd have to basically put it to each term. So remember, we do have to rewrite this. So first, let's deal with the top, because that's usually the thing we're trying to solve for. So we have to FOIL it. So first, let's do root of x plus 1 times root of x plus 1. Well, that just turns into x plus 1. The square roots will cancel. Then we have this one, the negative 2 multiplied by the root x plus 1. This gives you 2 times x plus 1. and then let's try the 2. So this will give you plus, so this is a plus 2, so a 2 times this 1 will give you a positive 2 times x plus 1. Notice that they're opposites of one another. That's important. And then we of course have 2 multiplied by a negative 2, which gives us a negative 4. So let's come back to that soon. For now, though, remember it's important to leave the bottom alone. Do not FOIL the bottom. It will work its way out if you just leave it be. And you'll see what I mean. So if we go ahead and simplify this, okay, what we can do is we can cancel these two. They're opposites of one another, so they will just kind of cancel each other out as 1. So now let's see what we have and see if we can do anything now that we've gotten rid of those two. Okay, so we have an x plus a 1 minus a 4 over the stuff on the bottom again. So we're just kind of carrying it over. So what happens is we can, of course, cancel out. We can 1 minus a 3 gives us an x minus a 3. And now you can maybe see where we're going with this. So if we have an x minus 3 on the bottom, and we have, remember, the same thing as before, the x plus 1 plus the 2, well, if you notice, the x minus 3's can now be canceled out. So what we really have is the limit as x approaches 3 of the 1 over the root of x plus 1 plus 2. And now we can solve this. There's no 0 on the bottom if we were to plug this in. So, for example, if we plug this in, we get 1 over the root of 3 plus 1 plus 2, which would give us 3 plus 1 is the square root of 4, which is 2, so we would get just 2 plus 2, which of course will give us just 1 over 4. So this whole thing works out to 1 over 4, and this is the answer to this limit. So now that we have a basic graph of the rationals and the standard ones, we can kind of work our way through something else. So these are the basic ways you have to simplify on, but there's also some other special ones you want to be aware of. So there are 2 special limits. The first one, and they're both trig limits. So we have the limit as x approaches 0 of sine of x over x. That gives us 1. Okay, and that's just kind of a special limit to know. And then we have the limit as x approaches 0 of 1 minus cosine of x over x, and that is equal to 0. Okay, and these are the 2 you're really going to use for a few of the problems if they give you these memorization ones. There's one other one that I like students to be aware of. It's this one. It's a little more complicated looking. So it's a limit as x approaches 0 of 1 plus x to the 1 over x, so this is an exponent, equals to e. So just e, the number. But this one isn't used nearly as much. It's just I like showing students to be aware of it. Okay, so these are the 2 that it's important to know. Okay, so I'm going to erase these, but they are 2 special ones. So we're going to do one for each of those special ones to give you an idea of it. So if we had something like the limit as x approaches 0 of sine of, let's just say 3x over x, what would this be? Well, we know that the sine of x over x is 1, so could we do anything to this to turn it into that? Well, we should note, first of all, that if we just had like a sine of u over u is still equal to 1. So it doesn't really matter what the coefficient is per se, it just they need to be the same value. Okay, so knowing that, what should we do? Well, the best thing to do is actually to multiply both the top and the bottom by 3. What we get then? What we'll end up getting is limit as x approaches 0 of the 3, so we're just putting the 3 in the front, of 3x over 3x. So can we do anything right now yet? We can't, unfortunately. But what we can do is we can break off the 3 and do it like this. Now, you'll see some teachers like putting the 3 in front of the limit, and some don't matter. It doesn't matter what you do. For the sake of you seeing it, I'm going to put it like next to the initial expression, but if you see it on the outside, that's perfectly fine as well. So if we move the 3 out of the fraction, but we're keeping it in the equation, in the actual equation, so sine of 3x over 3x multiplied by a 3 over 1, so again we just put the 3 out in the front. Well, now we can do it, because the limit as x approaches 0 of this function gives us 1. So this whole thing here is 1, and then multiplied by 3 is just 3. So the answer is 3. And usually you can see the answer, for sines especially, if you just look at the number in it. But to show your work, this is how you would do it. Okay, now we're going to try one with the cosine, which tends to be the easier of the two, just because 0 is a little bit, it usually will result in the answer being 0. Okay, so if we had the limit as x approaches 0 of 5 cosine of x minus 5 over x, what would we do here? Does this look like this expression at all? Can we do anything to make it look like this? So if we were to do this, what would you do? Well, it turns out the best thing to do is to take out a 5 from the expression, which is it's something we can do. So if we took out a 5, we would get the cosine of x minus 1 over x. Well, suddenly this kind of does look like our expression. So we're going to do what we did before, and we're going to separate it. So we're going to move the 5 out. So the cosine of x minus 1 over x multiplied again by this 5. And I don't have to put 5 over 1, just know that it is still the 5 here. So cosine of x minus 1 over x, we know that this is going to be 0. So this is 0. So 0 multiplied by 5 gives us 0. So the whole answer ends up being 0, which is usually what the cosine ones are, but this is how you show your work again. Okay, so these are what are called special trig limits. I like to just make sure you understand that just because it's a trig, it doesn't have to be a special trig limit. That's only if it's 0 and that kind of rational thing. It doesn't have to be. Okay? So that's kind of the general idea. The last thing I want to do is I want to reintroduce the idea of the limits of infinite, so infinite limits, but in this time I want to show you kind of what it would look like with more examples. Okay, so let's just say we had something like the limit as x approaches 0 of 1 over x squared. Okay, so what will we do here? Well, for most of these infinite limits, you can't plug in the value because it's indeterminate, just like before. So we have to end up drawing a graph here. So let me go ahead and show you the graph. So it would be something like this. Okay, so the graph looks a little like this. So the asymptote's right there, and it looks like this. So if we said, what is the limit as x approaches it from the left? Well, that would be, if we follow the graph from the left, that would be positive infinity. And if we said from the right, well, that would also be positive infinity because they're both going the same direction. Okay, so the important part with infinite limits is I know it seems like you're using graphical ones, but the difference is that sometimes it can change depending on what's occurring. Let's try something involving maybe absolute value. So I gave you something similar to this before on the intro video, but I didn't actually specify what graph that was. So it looks something like this usually. This is the absolute value graph. So if we had the function absolute value of x over x, so the reason why we can't do the limit as x approaches 0 is because it's undefined again. But if we said from the left, well, from the left, it looks like we have the value of -1. And from the right, it looks like we have a value of +1. And this would remain the same even if we changed the equation slightly. Okay, the last thing I wanted to show really quick is what if we have limits that are interesting? We're combining a lot of things. So what if we combine the infinite idea, the discontinuity idea, with just a standard algebraic situation? So let me show you what that might look like. So let's just say we had something, let's just say we're using 0, because that's sometimes nice to work with. 0 from the right of the value or the expression x squared minus 2 over x. But what would we do here? Well, we can't plug it in, not yet, because obviously if we put a 0 here, we'll get it'll be undefined. So instead what we want to do is we want to break this up. So before we break it up though, let's try to help with the part that it is hard to understand. So it's this 2 over x that's ruining everything. So let's, on the side, what would this be if it was just 2 over x? So if we had 2 over x, remember that's basically like 1 over x, we're just kind of adding a coefficient. Okay, so 1 over x would look something like this, okay? And we're looking from 0, so right here, from the right. So from the right would be here, and we'll be going off to positive infinity, up, up, up. So what we want to do now is we'll break it up. So we'll break it up as the limit as x approaches 0 from the right of x squared, and we want to subtract, so minus, the limit as x approaches 0 to the right of the 2 over x. So now we can find both and then do it from there. So the x squared isn't a problem, right? 0 squared is just 0. There are no discontinuities there, but this is the one that's the problem, right? So minus the 2 over x, we already said that was going to be 0 from the right, was that infinity up here. So 2 minus a positive infinity would just be 0 minus infinity is just going to be negative infinity. So the answer here is is negative infinity. And the key to solving equations where we have to combine algebra from before, so the plugin, and problems with finding it with graphs and other things, is we have to do it step by step. Okay, so let's try one more similar to this so we can get a really good grasp of it. And I may do a video at a later time doing more of these because these tend to kind of combine everything that's a problem with students sometimes doing these. We can go from there. So let's just say we had something like the limit as x approaches 1/2, right, of x squared. Ooh, my apologies, that's not a very good x squared. So x squared multiplied by the tangent of pi or x pi. Okay, so this seems to be difficult to do, but what we want to do is we want to simply use the same thing. So let's break it up first of all. So of a half of this x squared. Instead, we're just going to be multiplying it instead of adding it. That's the only difference. Multiply by the limit of x approaches 1/2 of the tangent of x pi. So now what we can do is on the side, we can tell that the tangent of that is, we unfortunately cannot, the half in this case would give you an undefined value. So tangent doesn't exist at that time, but what we can do is we can simply find that graph. So that would be something like this. So if we did the tangent graph, we know it would look like this. We go, it kind of looks like a cubic graph, and it has two asymptotes. It doesn't matter that we've shifted slightly from the parent function, it still works. So from this new graph, we know that it's going to be 1/2 is the asymptote here instead of 1. Apologize, instead of pi. And the other one would be a negative 1/2. And so if we went ahead and said 1/2, and that's all it's asking. Oh, I apologize. It was supposed to be 1/2 from the left. So let's add that. So a half from the left would be, if we went from the left, we went up, we wanted to, what happens to when we reach 1/2? Well, that gives you a value of infinity. So now we can kind of plug this in. So 1/2 squared. So let's write that really quick. So 1/2 squared multiplied by, we said that was going to be a positive infinity. So multiplied by positive infinity. So now we can solve this. So that's going to be 1/2 squared is 1/4 multiplied by infinity. Well, anything multiplied by infinity is just infinity. So the answer turns out to just be infinity. So this is kind of what you could expect solving problems that combine a bunch of the techniques. We're really just wanting to remember to break up the problem and solve from there. Sometimes you deal with multiple things of graphs, sometimes you deal with nothing. And the last thing I want to show you is kind of a trick one where they're pretending like you have to do the same thing. So let's pretend we had something like x approaches 0 from the right of e to the x multiplied by sine of x. Do we have to use our strategy from before? We don't, because if we can we plug it in? Let's see. Always see if you can plug it in. So e to the 0 power multiplied by sine of 0. So we know that e to the 0 power is going to be 1, and we know that sine of 0 is just going to give you 0. So the answer turns out to just be 0. Okay, so that's kind of the basis of a lot of the analytical things you'll see for the most part. There are a few other situations that are very, very rare. I'll go over it with a few other things in a future video, but I don't want to make this too long. So I hope this helps with analytical solving.